I want you to picture something for a second. Imagine a standard-sized door, just, regular entrance to a building.
Okay, I'm picturing it.
Now, imagine millions of people, like a massive crowd stretching just as far as the eye can see, and they all decide to walk through that exact same door at the exact same millisecond.
Oh, wow. Yeah, that's not going to work.
Right. What happens? Chaos. In
Yeah.
a massive bottleneck. Nobody gets in, nobody gets out, and the entire physical system just, it grinds to a complete halt.
Yeah, and when you strip away all the complex code and the network topology and the glowing screens, that is exactly the foundational mechanism of a denial-of-service attack. It's basically the weaponization of congestion.
The weaponization of congestion. I like that. And that terrifying, chaotic traffic jam is the essence of what we are unpacking today. We're doing a deep dive using the actual blueprints cyber professionals use to fight back, which is the official Certified Ethical Hacker, or CEH v13 curriculum documents.
Which is some pretty heavy, fascinating material.
It really is. And our goal here is to look past those tired Hollywood stereotypes. The lone hacker in a dark hoodie furiously typing in a basement. We're exploring the sophisticated corporate-like syndicates driving these attacks, the brilliant and terrifying ways they manipulate internet protocols, and how tech giants defend against, history-making digital gridlock.
Yeah, but before we get into the mechanics of the internet protocols themselves, we should probably establish a crucial distinction from the curriculum. We're really talking about two related but distinct threats here.
Right. The DOS versus DDoS.
Exactly. So there's a DOS attack, which is denial of service, and a DDoS attack, which is a distributed denial of service. A standard DOS attack is a one-on-one fight. It's one attacker using a single system to try and overwhelm a target.
Which I imagine has its limits.
It does. But a DDoS attack that leverages a distributed army of compromised computers, all scattered globally across the internet.
And looking at the sources, the primary goal for these armies, it usually isn't theft. I think that's a huge misconception. They aren't trying to break into a vault to steal your credit card data. The goal is just to block legitimate users.
Right, it's about disruption.
Yeah, it's causing massive financial, reputational, and operational pain by basically boarding up the digital windows of a business with junk traffic. You're keeping the paying customers out of the store.
They just flood the victim's infrastructure with non-legitimate service requests to completely exhaust its resources. But generating that staggering level of firepower, we're talking millions of requests per second, that requires serious infrastructure.
You can't just do that from a MacBook in a coffee shop.
No, definitely not. You cannot orchestrate a modern DDoS attack from a single laptop. You need an established, massive network of enslaved devices, which is commonly known as a botnet.
Okay, let's unpack this botnet concept, because this is where the lone wolf hacker myth really falls apart for me. The CEH documents actually lay out an organizational chart for modern cybercrime, and it looks like, a corporate hierarchy at a Fortune 500 company.
It really does, yeah.
Why do they structure it this way?
It really comes down to risk mitigation and the specialization of labor. Modern cybercrime operates on a highly compartmentalized revenue-sharing model. So at the very top, you have the boss.
Like a mafia boss.
Kind of, but the boss functions strictly as a business entrepreneur. They set the strategy, they source the funding, and they identify the ultimate targets. But, and this is key, they completely isolate themselves from the actual technical attacks to avoid legal exposure.
They're the CEO of chaos, basically keeping their hands totally clean.
Exactly. And underneath them is the underboss, who acts sort of like the chief technology officer. Their job is maintaining the infrastructure.
Meaning what, exactly?
Setting up the command and control servers, managing the databases of malicious toolkits, that sort of thing. But the real engine of the operation relies on the campaign managers.
Which the sources describe as basically middle management. But why do you need middle managers in a cyber attack? This seems so bureaucratic.
Well, because writing brilliant malware and effectively distributing that malware are two completely different skill sets. The developers who create the malicious code often lack the network or the business acumen to infect 1 million devices.
Oh, interesting. So they're just the engineers.
Right. So the campaign managers step in, they rent the botnet infrastructure, and use affiliation networks to distribute the malware at scale. It allows the coders to focus on code, while the managers focus on aggressive distribution.
It's like a cybercrime as a service gig economy. It's wild. But to run this business, they need raw materials. They need the actual devices to form this army of zombies. How are they tricking unwitting people's devices into moonlighting as cyber mercenaries at such a massive scale?
Yeah, that's where it gets scary. They rely on highly automated scanning and infection techniques that compound over time. The curriculum highlights hit list scanning as a prime example of this.
Hit list scanning, how does that work?
So, the attacker compiles a pre-researched list of potentially vulnerable machines, say thousands of servers with a known unpatched software flaw. They infect the first machine, and then they split the remaining hit list in half.
Okay, I'm tracking.
The original attacker scans one half, and the newly infected zombie machine simultaneously scans the other half.
Wow, so it's exponential growth. Every time they break into a house, that house immediately starts looking for more open doors.
Exactly. The number of compromised machines doubles with each successful cycle, so they consume a massive hit list in a surprisingly short window. But the challenge attackers face at that scale is redundancy.
What do you mean?
Well, if you have 100,000 zombies indiscriminately scanning the internet for new victims, they are inevitably going to bump into each other and waste time trying to infect machines that are already infected.
Right, if they're all just guessing random IP addresses, the overlap would be huge. The sources mentioned they solved this using permutation scanning and a 32-bit block cipher.
Yeah.
I've got to be honest, a 32-bit block cipher sounds incredibly dense. What is actually happening there?
I know, it sounds like pure math jargon. But think of the 4 billion possible IPv4 addresses on the internet as a standard deck of playing cards. A 32-bit block cipher is basically just a cryptographic algorithm that shuffles that massive deck into a specific mathematically predictable order using a secret key.
Okay, so it's a perfectly shuffled but predictable deck.
Right. Every single zombie in the botnet is given that exact same shuffled deck. But each zombie starts drawing cards or scanning IP addresses from a completely different random starting point in the deck.
Oh, I see. So they're all working through the exact same list, just starting at different chapters.
Yes, exactly. And here is the brilliant part. Because they are all moving through the same sequence, if a scanning zombie encounters a machine that is already infected, it instantly knows that another bot has already been down this path.
Wow. So it doesn't even waste its time.
Nope. It immediately drops its current sequence, jumps to a brand new random starting point in the deck, and resumes scanning.
That is disturbingly clever. I mean, they guarantee total coverage of the internet with zero redundant work, and they don't even need a central server coordinating their movement.
It's incredibly efficient.
And this army isn't just made of desktop computers, right? The sources point out a huge growing target, which is unsecured Android devices.
Yeah, the mobile threat vector is expanding rapidly. Attackers are taking legitimate-looking Android application packages, APK files, and injecting malicious server code into them.
Like fake apps.
Or even real apps that have been modified. They encrypt the payload to bypass standard security permissions and then distribute these poisoned apps on third-party app stores. Or occasionally, they even slip them past the defenses of the Google Play Store.
So a user thinks they are just downloading like a free flashlight app or a puzzle game, but the moment they install it, their phone is silently conscripted into this global army.
Yep.
It's sitting in their pocket launching cyber attacks, and they have absolutely no idea.
Well, aside from maybe noticing that their battery is draining a bit faster than usual due to the background processing, yeah, the user is completely oblivious to their device's participation.
That is terrifying. Okay, so you've got this massive corporate-run army of 1 million smartphones and compromised servers secretly awaiting orders. How do you actually point that weapon? Because they can't all just be mashing the refresh button on a single website, right? They must have different tactics for different targets.
They absolutely do. The arsenal is really diverse. The CEH v13 curriculum categorizes these attack vectors into 3 primary groups, which are volumetric attacks, protocol attacks, and application layer attacks.
Okay, let's look at volumetric attacks first. Based on the documentation, this is pure, unadulterated brute force. The goal isn't to be clever. It's just to create a tidal wave of data measured in bits per second to completely clog the target's bandwidth.
Right. It is the digital equivalent of trying to shove a bowling ball through a garden hose. But attackers have found ways to magnify that force. A classic example from the curriculum is the NTP amplification attack.
NTP?
Yeah, that utilizes the network time protocol, which is the system that synchronizes the clocks on computers globally.
I found this part fascinating because it's not just about sending traffic. It's about tricking the internet's own infrastructure into multiplying your attack power. But there's a technical nuance here I want to get into.
Sure.
The sources say the attacker uses their botnet to send a very small UDP packet to the NTP server with a spoofed IP address. Why a UDP packet specifically?
That is the linchpin of the whole operation. So the internet largely runs on 2 main protocols for sending data. TCP and UDP.
Okay.
TCP is like making a phone call. It requires a connection, like a back-and-forth handshake, to verify both parties are who they say they are before any actual data is exchanged. UDP is entirely different.
How so?
UDP is like dropping a letter in a public mailbox. It is connectionless. You just send the data and hope it arrives.
Oh, I get it. Because there's no handshake to verify the sender, an attacker can easily forge the return address on that digital envelope. They write down the victim's IP address instead of their own.
Exactly. The botnet sends thousands of these forged UDP packets to a vulnerable NTP server. And inside those packets is a specific diagnostic command called monlist. This command asks the time server to return a list of the last 600 IP addresses that connected to it.
Okay, let me try an analogy here to see if I have this right. It's like mailing a standard lightweight postcard to a massive company, but you forge the return address so it looks like it came from your worst enemy.
Ah, yeah, that works.
And on the postcard, you ask the company to mail back their entire 1,000-page product catalog. So you spend a tiny amount of energy sending a postcard, but your enemy gets completely crushed under a pallet of heavy catalogs.
That perfectly captures the asymmetry of an amplification attack. The time server processes that tiny monlist request and generates a massive response. We're talking sometimes hundreds of times larger than the original packet.
And because the return address was spoofed, it hurls all that data straight at the victim's network.
Precisely.
But wait, if I'm the victim being crushed by these catalogs, or I guess if I'm the time server suddenly sending out thousands of them to one guy, why doesn't the server just block the guy asking for them?
Well, because from the time server's perspective, it isn't an attack. It sees a perfectly formatted request coming from the victim's IP address. It thinks the victim genuinely wants that data.
Oh, man.
Yeah, the server is just dutifully fulfilling what looks like a legitimate administrative request.
Wow. Okay, so volumetric is basically dumping a mountain of junk on the lawn so nobody can get to the front door. But what if the attacker wants to break the house itself? That transitions us to the second category, which is protocol attacks.
Right. While volumetric attacks target pure bandwidth, protocol attacks target the underlying network infrastructure. We're talking firewalls, load balancers, application servers. They aim to consume connection state tables, and we measure their severity in packets per second.
And the prime example here from the curriculum is the SYN flood attack, right? Which exploits that TCP handshake we mentioned earlier.
You got it.
Let's break down that TCP three-way handshake really quickly. Normally, if my computer wants to talk to a server, I send a SYN packet, basically saying, hello, I'd like to connect.
Right.
The server receives that, allocates some memory for our conversation, and sends back a SYN packet saying, hello, I hear you, I'm ready. Finally, I send an ACK packet saying, great, let's talk, and the connection is established.
Exactly. So in a SYN flood, the attacker manipulates that courtesy. They send a massive wave of those initial SYN requests, again utilizing spoofed IP addresses so they can't be traced.
Okay, so a wave of fake hellos.
Yeah. The target server receives this flood of greetings, allocates memory for every single one, sends back the SYN responses, and waits for that final ACK to complete the connection.
But the final ACK never comes, because the original requests had fake return addresses. So the server is enthusiastically extending its hand to an empty room. It's essentially starting a handshake, waiting for the other person to extend their hand, and the attacker just turned around and walked away.
That's a great way to put it. And the problem is the server is hard-coded by its operating system to be patient. It places that half-open connection into a specific memory bank called a listen queue, and it waits for up to 75 seconds for the final response.
75 seconds in internet time is an eternity.
It is. If an attacker sends enough of these incomplete handshakes quickly enough, that listen queue completely fills up. The server has literally zero memory left to track any new connections.
So when a real, legitimate user comes along and tries to log in, the server ignores them because its hands are completely full holding onto ghost connections. It paralyzes the system without needing the massive bandwidth of an amplification attack.
Which brings us to the third tier of the arsenal, the application layer attacks. These operate on layer 7 of the OSI model, targeting specific applications like web servers. And we measure these in requests per second.
If volumetric is a tidal wave and protocol is a traffic jam, these feel like stealth assassins.
They really are surgical. What makes application layer attacks so dangerous is that they do not require massive botnets, and the traffic they generate looks perfectly legitimate. This makes them incredibly difficult for standard firewalls to identify and block.
And a standout example from the CEH curriculum here is the slow loris attack.
Yes.
It's such an unassuming name for something so destructive.
It is. Slow Loris is really a masterpiece of malicious efficiency. Instead of flooding the server with traffic, the attacker opens multiple connections to the target web server and sends HTTP requests incredibly slowly.
How slowly are we talking?
Well, they send a partial request, just a fragment of a standard web header, and then they pause. Just before the server's timeout window is about to close, they send another tiny fragment.
Wow, they are just drip-feeding data to keep the connection on life support.
Exactly. The web server thinks, well, this user must just be on a terrible, slow internet connection. I will hold the line. But eventually, the attacker exhausts the server's maximum concurrent connection pool. The server is entirely occupied waiting for these excruciatingly slow, fake requests to finish.
But why wouldn't a firewall catch a guy taking 4 hours to send a single request? That seems so suspicious.
Because taking a long time to send a request isn't a violation of the HTTP protocol. It's not illegal. The traffic is perfectly formatted. It isn't triggering any volume alarms, and it isn't exploiting a technical bug.
It's just abusing the rules.
Yeah, it is simply abusing the server's designed willingness to wait. It is the digital equivalent of someone going into a busy coffee shop, placing a single napkin on every single empty table, and telling the barista they are still deciding on their order for hours on end.
Huh?
No actual paying customers can sit down, but the person hasn't technically broken any rules.
That is infuriating, but brilliant. Now, here's where it gets really compelling. We've talked about the theory and these mechanics kind of in isolation. Let's look at what happens when these concepts collide with real-world infrastructure.
Sure.
The source documents detail a case study about an attack on Google Cloud in September 2023, and the scale is almost difficult to wrap your head around.
Oh, the rapid reset attack. Yeah, Google's DDoS response team absorbed an attack that peaked at an astonishing 398 million requests per second.
398 million requests.
Yeah.
Every single second.
Yeah. To put the magnitude of that into perspective, it was 7.5 times larger than any previously recorded attack in internet history.
That is just staggering. But it wasn't just the size, right?
Right. The size was historic, but the technique was what truly alarmed the cybersecurity community. This wasn't a standard brute force volumetric flood. The attackers uncovered and weaponized a novel vulnerability in the HTTP2 protocol, a technique known as rapid reset.
And the irony here is thick. HTTP2 was specifically designed and globally adopted to make the internet faster and more efficient.
Right. Yep. It introduced a feature called stream multiplexing. This allowed multiple streams of data to be sent concurrently over a single TCP connection rather than making them wait in line.
But the attackers turned that efficiency against the protocol itself.
They did. They exploited multiplexing by initiating a massive number of concurrent streams, but then instantly sending a RS stream frame, which is a cancellation command, for every single one. They were essentially yelling start, stop, millions of times a second.
Wow. They forced Google's servers to expend massive computational CPU and memory resources, constantly setting up and immediately tearing down connections that were never actually used. How do you even fight something that massive? I feel like a standard corporate firewall would just melt.
Oh, a standard firewall would be gone instantly. You have to absorb it at a global scale. Google mitigated it by using their edge network capacity. They were essentially leveraging their massive global footprint of servers as a giant sponge to soak up the malicious requests before they could hit the core applications.
And the broader industry response detailed in the curriculum is fascinating here. Google realized this vulnerability threatened the entire internet, not just them.
Yeah, they spearheaded a massive collaborative effort across the tech sector. They quietly worked with other cloud providers and software maintainers to develop patches for this vulnerability, which was designated as CVE 2023-44487.
So they coordinated a responsible disclosure only after the major players had mitigation strategies in place.
Exactly.
It really was an Avengers-level team-up for cybersecurity.
Yeah.
But while Google was fighting temporary disruptions on a global scale, the curriculum contrasts that with something much more intimate and, honestly, destructive. Permanent denial of service, or PDS.
Yeah, often referred to as flashing. This is a total paradigm shift. The goal is no longer temporary unavailability. The goal is the permanent physical destruction of hardware.
Right. If a standard DDoS is like blocking the entrance to a restaurant so nobody can eat, PDS is like sneaking into the kitchen and setting the entire building on fire.
Yeah, you can't just wait for the crowd to disperse. You have to rebuild the restaurant from scratch. PDS attacks sabotage the system hardware, forcing the victim to physically replace or manually reinstall the device.
How do they actually physically break it from across the internet?
Attackers achieve this by exploiting security flaws in device management interfaces. The administrative portals on routers, printers, or enterprise networking equipment, they use a technique known as bricking.
Literally turning a $10,000 enterprise router into a useless brick. And they do this by pushing fraudulent firmware updates, right?
Exactly. A network administrator might be tricked by a phishing email into clicking a link, and suddenly their core router downloads corrupted software that permanently overrides and destroys its own operating system.
That is brutal.
It is. It requires a fraction of the resources needed for a massive botnet attack, but the damage is immediate. It is irreversible without physical intervention, and it is catastrophic to an organization's daily operations.
Well, we have covered a massive spectrum of threats today.
Yeah.
We've seen that denial of service is not just one blunt instrument. It ranges from the pure brute force bandwidth exhaustion of an NTP amplification to the surgical slow drip suffocation of a Solaris attack, all the way to the historic protocol-breaking scale of the HTTP2 rapid reset exploit.
And the common thread is that these operations are run by sophisticated, highly structured crime syndicates. They're utilizing automated, mathematically elegant infection methods capable of threatening both global internet giants and the vulnerable smart devices sitting right in our living rooms.
It's a lot to process, but I want to leave you, the listener, with a final thought to mull over based on something tucked away near the very end of our source documents. The curriculum outlines several DDoS attack toolkits that are freely available online. We're talking about tools with names like Ultra.SV2, High Orbit Ion Cannon, or HOIC, and one literally called ISB, which stands for I'm So Bored.
Yeah, the screenshots of these tools in the curriculum are honestly the most concerning part for me. They are not complex, text-based command line interfaces that require a computer science degree to operate. They feature simple, intuitive, graphical user interfaces.
Like, incredibly simple.
An attacker simply types in the target's IP address, selects the attack vector from a convenient drop-down menu, and clicks a button to launch the attack.
And that is the provocative reality I want to leave you with. The tools required to launch devastating attacks on global infrastructure now feature user-friendly, point-and-click interfaces. At the same time, our everyday smart devices, our phones, our TVs, our refrigerators, are easily recruited into these zombie armies without us ever knowing. So are we moving toward a future where the stability of the internet relies entirely on the self-restraint of the masses, rather than the advanced firewalls of tech giants? Think about that massive crowd standing outside the standard-sized door. What happens when everyone in that crowd realizes they hold the key to the lock, and they are just one simple mouse click away from trying to walk through with the exact same millisecond?